Miss Courtney, and we are reading in our science book on page 211, section 8.2, water vapor, the key to weather. When you think about weather, you do not usually consider the rotation of the earth or the winds that circulate over the tropics. You are more interested in today's forecast in your area. Will it rain or snow? Is the sun going to shine today, or will the sky be cloudy? Will it be cold enough to wear a jacket? You want to know the forecast because local weather conditions can greatly affect many of your day-to-day activities. For example, a little bit of rain might determine whether or not you will be able to play outside after school. In the last section, we talked about the different seasons, temperatures, and winds that are found across the Earth's surfaces. These things make up weather's big picture. Now we are going to zoom in to take a closer look at various types of weather as you could observe them from the ground in your own hometown. The smaller building blocks of weather include such things as clouds, rain, snow, and storms. They depend upon another essential ingredient of weather, which is water vapor. But before we can go on to learn about clouds and storms, we need to talk about how water vapor behaves when it is mixed with the air. Humidity. Humidity is relative. The air we breathe contains a small amount of water vapor. Depending on the temperature of the air, there is a limit on how much water vapor the air can hold. Warm air can hold much more water vapor than cold air can. We refer to the amount of water vapor in the air as the humidity of the air. Humidity is measured by a percentage. If the humidity is 75%, for instance, that means that the air contains 75% of the water vapor it is able to hold at that temperature. If the humidity of air is 100%, we say the air is saturated. Saturated air at a particular temperature contains the greatest amount of water vapor air can hold at that temperature. A humidity measurement tells us how full of water vapor the air is. Because warm and cold air are able to hold different amounts of water vapor, the humidity percentage is a relative measurement. That is, it is relative to or based upon the temperature of the air. We refer to the measurement of humidity as the relative humidity. It takes more water vapor to produce a humidity reading of 100% at a high temperature than it does to produce the same reading at a low temperature. For instance, saturated air at a temperature of 90 degrees Fahrenheit contains much more water vapor than the same amount of saturated air at a temperature of 30 degrees Fahrenheit. But both quantities of air have a relative humidity reading of 100% because they both hold as much water vapor as they possibly can at their different temperatures. The dew point. As air cools, it loses some of its ability to hold water vapor. Let's imagine we have a room full of very warm air at 45% relative humidity. If we cool the room down a few degrees, the relative humidity will rise, say to around 60%. The amount of moisture in the air has not changed, but the total amount of water vapor the air can hold has been decreased. Therefore, although at the warmer temperature the air was only 45% full of water vapor, at the cooler temperature the air is 60% full. If we continue to lower the temperature of the air in a room, the relative humidity of the air keeps on rising. Eventually, the relative humidity reaches 100% and the air becomes saturated. The temperature at which cooling air becomes saturated is called the dew point. The dew point is not one fixed temperature. Rather, it varies depending on how much water vapor the cooling air contains. Air that contains a large amount of water vapor will have a higher dew point temperature than air that contains a very small amount of moisture. The air in the room started out with a relative humidity of 45%. Its dew point temperature is higher than it would be if it had begun with a lower relative humidity of 30%. Condensation. The dew point is the lowest possible temperature at which air is able to hold on to all of its water vapor. If saturated air continues to cool below its dew point, it must release some of the vapor. Released water vapor leaves the air and changes back into liquid water in a process called condensation. We see the results of condensation around us all the time. Have you ever sipped a tall glass of lemonade on a hot day? If so, you have probably noticed that the outside of the glass becomes very wet. No, that moisture is not lemonade oozing out of a crack in your glass. It is pure water, released through condensation when the hot, humid air surrounding the glass was suddenly chilled by coming into contact with the cold glass. The hot air cooled below its dew point, deposited in its excess water vapor as a liquid onto your glass. Riding in the car with your family on a cold night, you may wonder why the windows are all fogged up. Again, the cause is condensation. The breath of the people in the car makes the air inside much more warm and moist than the air outside of the car. When the humid inside air is cooled below its dew point through contact with the cold glass, the result is a thin, misty layer of water on the inside of the window. During the day, the Earth's surface absorbs heat from the sun. Then at night, the Earth radiates this heat back into the atmosphere. As the ground gives off heat, it cools faster than the air above it. And the temperature of the ground drops quite a bit lower than the temperature of the air. The warmer air just above the ground is cooled by contact with the cold ground. What do you suppose happens when this air is cooled below its dew point? You can guess easily enough. Dew forms on the ground as the water vapor in the air condenses. If the temperature of the ground is below freezing, the water vapor freezes, forming frost on the ground instead of dew. And we will stop there for our comprehension check.